Okay, our third speaker, Adam Elmachtoub from Columbia University. He leads a team that wrote a paper and is a finalist. It's called Pricing Analytics for Rotable Spare Parts.
Good morning, everyone. Thank you to the Wagner Prize Committee for all their hard work. It's a very long process for those who don't know, and it's a lot of work, so thank you very much. And it's been very nice watching the other presentations. Also 10 out of 10 on the name pronunciation. Thank you, Mary. So I want to acknowledge this is joint work with my co-authors, Omar Besbes, who is at the Columbia Business School. I'm in the engineering school at Columbia, and my PhD student, my former PhD student, Yunjie son. And a little bit maybe unusual for this prize, but our industrial partner is anonymous here. And maybe this is mixed news, but the reason why they're anonymous is because they're so happy with the tool that they're actually quite afraid of other people learning about it, and specifically their competitors. So they withdrew their official, their title here, but nevertheless, we'll pretty much tell you everything that happened, except their name. So before I get into the fine-grained details, I want to say, so this is a project about rotable spare parts, which might seem very specific. It in itself is a very large industry, but actually the entire project applies to a general class of problems known as reusable resources. I'll just briefly mention a little bit about this, and then we'll focus on rotable spare parts. So a resource is reusable, basically, if it can be used by one customer, and when the customer is completed with the service, another customer can use it. So many examples include hotel rooms or airline seats, cloud computing, and anything in the sharing economy, and so on. What this project is about is rotable spare parts. Okay, so what is a rotable spare part? It's a reusable resource. And this is a part and a very expensive part typically, that when it breaks, you don't dispose it, you actually repair it. And what you do is, when the part breaks, the customer will buy a new part from the manufacturer, but they do an exchange sale. So the customer gives the manufacturer the broken part, the manufacturer gives the customer a functional part. And then the manufacturer takes the broken part and then repairs it and eventually sells it to another customer. Okay? So here's an example of a rotable spare part called the thrust reverser on the bottom, and that's the warehouse containing a lot of rotable spare parts. Okay. So who is our industrial partner? It's a major aircraft manufacturer. We may or may not be in one of these in the middle of the air. I don't know. That's my PhD student, Yunjie. You may be wondering where Omar is. He's actually flying the plane. I'm just kidding, he's not. But this is a major company. It's been around for quite a while, and they have thousands of aircrafts in the world. And a key mission for them is to maintain service for all of their aircrafts, including and all the parts. So they have many different models dating back 50 years. So here are some of the very interesting challenges at this aircraft manufacturer. So first of all, they have thousands of different kinds of parts. Each of them vary in the time it takes to repair, the cost, the amount of inventory they have, and so on. And for many of the parts, there's actually competitors that sell those parts. So it may seem unusual, how could a competitor exist for something like airplanes? What happens is basically other competitors get their hands on one of these airplanes, they dismantle them, and then now they have a whole business. So they can actually buy old airplanes and turn them into spare parts, and you only need one part to have a business because it's reusable. You can sell it over and over and over again. And another really big challenge is, although we're in the world of big data now, this is an extremely limited data environment because many of these parts last quite a long time. So you might only change a part every 10 years or so. And therefore, the amount of data you have per rotable spare part is very, very small. So this is a very slow-moving industry. On top of that, you have competition, so you can't even observe all of your demand. So the goal for this project was they basically came to us and said, look, we're doing really bad in our Rotable spare parts business, and we would like to make this better. And what we want to do is develop a dynamic pricing solution to increase our overall profit. Okay? And basically, one of the key aspects of that is we want to take advantage of our inventory. So when we have low inventory, we feel like we should price higher. When we have higher inventory, we feel like we should price lower. Okay. And I put dynamic there in parentheses because at the end of the day, that's not actually what happened. So I'll explain later about that. Okay, the objective is basically to maximize profit, but we also care about things like service level and market share. Service level is what's the fraction of time that we actually have the unit in stock. So this is important because you don't want to tell your customers that when they come to buy from you that you don't have the product available. And market share is quite important because you don't want to start selling less at the cost of a higher price, because it's important for you this company to interact with their customers as frequently as possible, because it leads to a higher chance of them buying a new aircraft down the road. Okay, so these are sort of soft things that are hard to capture directly, but we implicitly capture them through things like service level and market share. So here's a sort of large overview of the research, which is a several-year process starting in 2016. So it took quite some time to get the data and design the model and find out all the business constraints that were relevant. And all this led into the price optimization solution, which I'll describe in a lot more detail. Given the limited data environment we're in, it's very, very important to consider sensitivity analysis and what we call price robustification, making sure that the prices we're going to suggest actually make sense and they're robust to many of the uncertainties that we found. Then we actually designed a controlled experiment, which was quite a political process, but I'll explain a little bit about that. And we actually did a live implementation, and currently this is rolling out to all of the Rotable spare parts business as we speak. Okay, let me tell you about the data. So this data is, collecting this data was a nightmare, but it existed across multiple databases, and as I said before, the data is very limited and quite noisy with lots of recording errors. So lots of data cleaning went into that. And here's just a picture showing you what's the average number of units sold per year. So on the y-axis you have the number of Rotable spare parts. So in this picture you're seeing things like landing gear, engines, motors, all kinds of different parts, and this is a histogram counting the number of units sold per year. So you can see for almost like 75% of the parts, they sell less than 10 per year. Okay, so it's very slow moving. Actually, for over half the parts, they sell less than 5 per year. Okay, and I should say that actually they rarely ever change the prices. So there's actually it's very hard to estimate the price-demand relationship, because essentially they've used the same prices for many years for most of the products. So I'll explain how we dealt with that as well. Here's some more of the data. So on this histogram, you can see the number of units that we have for every single Rotable spare part. So this is also called the pool size. Okay, so pool size of 2 means they own 2 units of the part. Okay, and you can see the pool size is relatively small most of the time, often very less than 5, and many of the times around 1 or 2. Okay, here are 2 more histograms. This is showing you data around the service time, meaning how long it takes to repair, and this is a door-to-door time, basically, from including the time it takes to send to the repair facility and the time to come back. And we also have data on the inter-arrival time between customers. So what I'm plotting is actually the coefficient of variation. Okay, so I'm trying to show you all the data for all the parts simultaneously, and the key quantity I'm looking at is coefficient of variation of these inter-arrival times and service times. And the 2 things I want you to take away are, one is that the coefficient of variation is quite large. It hovers around 1, and it's always greater than 0.5. So this is a very noisy system. even the repair time is quite noisy, which was a big finding for us and even for them. And the second thing I want you to notice is that it often hovers around 1, even though these are noisy estimates, it hovers around 1, meaning that you want the choice of the distribution that we're going to choose is going to be an exponential distribution, which has a coefficient of variation around 1. So we're essentially justifying this sort of assumption here that in the aggregate, it seems like an exponential distribution works well. And there's more details in the paper about that, but this sort of crisply summarizes that. So that's a brief summary of the data. Let me tell you what the model is. So the model is very clean. It's can basically write on one slide. Okay, so this is a model that we implement for each rotable spare part individually. Okay, so this model is implemented thousands of times. So think of just one part, like a landing gear. So we describe C to be the total number of units. That's the pool size I told you about. Mu is the repair rate, and 1 over mu is basically the average time to repair. And we assume it's exponentially distributed. Little c is the average repair cost. Then we have lambda of p, which is the arrival rate as a function of the price. So this is a very important quantity. It's telling you what's the rate of customers arriving to me wanting to buy a product as a function of the price. Okay. Now, one sort of trick that's common in revenue management and pricing is to look at the inverse of this function, so p of lambda. So instead of making the decision variable to be the price, you can make the decision variable to be the arrival rate, and those two are equivalent. So P of lambda is going to be the inverse demand rate. And the reason we do this is because it's numerically easier to solve this problem. It's a concave optimization problem, and it also helps with our theoretical analysis. Okay. And given this kind of problem, it's not too hard to see that the optimal solution is a dynamic pricing policy, where I'm going to put a price for every possible inventory state. So there's going to be a price when I have C units available, there's going to be a price when I have C minus 1 units available, and so on. And you can see sort of this leads to a simple one-dimensional Markov chain that you can sort of visualize over here. So the objective essentially is to choose all of these prices, so the C prices, which is equivalent to choosing C arrival rates, in order to maximize some combination of your profit rate, your service level, and your market share. So that's the model. Okay, and on the top, I might forget to mention, but we're keeping track of the timeline of the project if you're curious. All right, let's actually do a little walkthrough of the model so we all make sure that we understand what's happening. So here's an example when I have 6 units of inventory, so the pool size is 6. And currently, right now I have 4 in my warehouse that are ready to be sold and 2 in my repair facility which are under repair. So a customer, under this setting, a customer may come. The current arrival rate is lambda 4 because I have 4 units available. This customer has a broken part. I sell them a functional part. They go away happy, and now I have this broken part. So I send it to my repair facility, and now I have 3 units. Okay, so now my arrival rate is lambda 3. Another customer comes. This person gives me their broken part. I give them a good part. This is the exchange sale. And then I send this off to repair. Now at some point, one of my parts ends up, finishes repair. It comes back to me. Now I have 3 units available again, and my lambda rate goes back to lambda 3, and so on. Okay? Now, so that's the model, and we want to solve this optimization problem, finding all the optimal prices. And as a simple sort of sanity test, we thought, why don't we compare the dynamic pricing solution to the optimal static pricing solution, where we just use one price instead of C prices. So this is a table that summarizes our results. And this table actually is actually showing you the worst possible case we found of static pricing versus dynamic pricing. And you could see these numbers are very, very high. So in the worst case, we were able to find that static pricing was only 2.5% worse than dynamic pricing. And that's assuming all the inputs are correct. Okay? So this was a very surprising finding. In fact, I accused my PhD student of having wrong code for several months until I believed this. Okay? So naturally, this led to 2 things. One, sort of had to put our tail between our legs, and although this company was funding us to do dynamic pricing, I had to kindly tell them, look, it doesn't actually make sense. We're going to do static pricing, but the right way, at least, incorporating this inventory dynamics. And two, it led to us thinking about, can we actually understand this theoretically? What is actually going on here? So this is a great thing about applied research. It often leads to theoretical research as well. So it's a nice interplay. So a brief detour about, can we actually prove this? I won't go into this too much. We actually have a theoretical paper on this for those interested. Little Game of Thrones joke there. Okay. All right, so can we actually prove this? And as I said before, it's important to show this because the results are so remarkable. In the literature, people have shown that static pricing is actually a good idea when the number of units is large. So in what they call large-scale systems, people have shown static pricing is optimal. But in our systems, the number of units was very small. It was often 2, 3, or 4 units. Okay, so we needed a new analysis to actually show that. Okay. And the other thing why it might be good to show this sort of guarantee is that if you're going to do dynamic pricing, you want to make sure that your demand model is good. And in this case, it's very hard to come up with a very strong demand model that we were confident in. But I'll get back to that in a second. All right. So maybe in the interest of time, I will skip some of this, but this is a simple way to describe the profit, market share, and service level. And what we do is describe these 3 quantities in terms of the steady state probabilities of the system. And what we do is we construct a static optimal solution that is basically our static optimal solution. What it does is it chooses the arrival rate such that the average number of customers arriving to the system is the same as the optimal system, conditional on there being at least 1 unit in this system. Okay. So the static arrival rate we choose is the one that leads us to having the same average arrival rate in the optimal policy, conditional when we're selling stuff at all. Okay. And what we can prove is actually that our static price solution guarantees us 15/19, which is around 79% of the optimal profit, market share, and service level all simultaneously. Okay. And this is a theoretical bound. So, and it holds over all possible instances. Any choice of C, arrival rate, and so on. So it's very limited assumptions. Okay. So this provides the evidence that we were looking for that this works quite robustly. Even still, the numbers we found numerically were in the 90s. So we decided, can we actually get a better bound? So we looked at a special case with just 2 units, which is actually a case we saw quite a lot with linear demand. And we can actually prove that in this case, we obtain a 95.5% bound. So we actually came remarkably close to that empirical finding. All right. So hopefully I've convinced you static pricing is a good idea. So let's see how we actually do this in practice. Here we go. So here's the big problem. How do you actually create a demand model if a company never changes the price? Okay, this is a surprisingly challenging problem. So this is where we're at. So we have one price that's being offered, and we know we can approximate the arrival rate under this price by looking back 5 to 10 years, which we did. But now you have to fit a curve. How do you fit a curve to one point? Okay, so this I will tell you, this took us 6 months to figure out, and we're trying many ways. And I will tell you also that the natural thing to do might be to look at competition and see what the competition is doing. And the company actually tried this and hired a consultant and paid them to get this information. It turns out it was all bogus information. You can also think about learning. Learning is a very hot topic where you experiment and do all this stuff, but it's actually impossible in this setting because the parts are so slow moving. By the time you learn the model, it will be a decade later. Okay, so that's not really feasible. So here's what we did. We basically worked with them to decide what is a price where you think you can fully capture the entire market. Okay, so what we did is we said the maximum of the repair cost and half the current price should lead us to full market share. Okay, and that gives us sort of a second point. Now, I do know how to fit a curve to 2 points. You just put a line through them. Okay, so this is what we did. We basically worked with them to decide what is a price where you think you can fully capture the entire market. Okay, so what we did is we said the maximum of the repair cost and half the current price should lead us to full market share. Okay, and that gives us sort of a second point. Okay, that's what we did. Okay. So now the problem of fitting demand curve boiled down to estimating their current market share, which in itself was quite a challenge and required many techniques. But ultimately, we picked one, and we allowed the user to really adjust this in the tool, because it was still, although we picked a reasonable approach, it still required some manipulating for some parts. Now, when we use our tool to solve for the optimal static price, as I said before, it could be sensitive to the inputs because they're quite noisy. So we ran many scenarios accounting for the noisiness and the estimated parameters. And we also tried out different prices. So what we did is we picked 3 candidate prices corresponding to the optimal price and a price that led to 95% of the optimal revenue. So a little bit to the left and a little bit to the right of the optimal points on the profit curve. And we said which one of these prices worked best overall across the thousands of scenarios, and that's the one we picked. So this is our decision support tool. You could see that on the left, you select the part, and then you get some information about the part. You can see this is the inputs we estimated directly from the data. All of these inputs can be overridden, and sometimes they were. In particular, the minimum market share and maximum market share as well. You press calculate, you get some price changes. So in this example, the suggested price change was a reduction in 21% of the price. And there's also, this is describing the price robustification approach, where we where the tool automatically plays with all these parameters by looking at the standard deviation of those inputs, and then finds the most robust price. And this is visualizing all the data together and all the price changes across all the scenarios. So you can see that in this example, all the price changes were negative. So although you may not believe all the model's details, it was very clear for this part and many parts whether to increase the price or decrease the price by seeing this visualization. Okay, so I'll wrap up in just a couple minutes. So this controlled experiment that we did, we basically bucketed all the parts based on their usage and the suggested price changes, and evenly split them into a test group and control group. Okay. And one important detail of this implementation is that we never advertise to the customers which parts were actually changed price. Okay, so this is to make sure we didn't bias the data. We just generally said that there is a new general pricing program. You should check out the website, and that was pretty much it. So they had generic advertising as to not affect individual parts. So this is the sort of major business findings, I guess, that after doing an implementation and observing the demand data for 10 months, which was around 200 working days, we generally observed a 3.9% increase in profit, which was quite substantial and on the order of millions of dollars. We also did some sensitivity analysis on this estimate in itself. This is a difference in difference estimate. And on the lower end, it was 3.61%. Okay, so our findings were quite robust, and the solution worked quite well. And it's currently being implemented at the company now. And I should say it's completely changed the pricing culture and has led to many other projects and funding and hiring and general belief in the power of analytics. So it's been quite successful overall. And we believe this sort of, this model can be applied to other reusable resource settings and hopefully provide some insight on how to implement this in practice as well. Thank you very much.